Hi, this video will cover an introduction to reciprocating engines and the Otto cycle. Here's an example of a reciprocating engine. In this case, it's an automotive engine. And you can see a cutaway with all the parts inside. So here we have a piston inside a cylinder, and there are several valves for each cylinder that control the inflow and outflow. Here's the crankshaft, which the pistons are connected to by connecting rods, which turns for power. The timing belt connects the crankshaft to the camshafts, which then control the valve timing. Here's a diagram of an engine cylinder, and you can see that there's several terms labeled here. So there's the piston inside the cylinder. We have the diameter of the cylinder is called the bore, and the stroke is the length which the piston moves up and down, from the top point, which is called top dead center, to the bottom point, which is called bottom dead center. Here's showing the volumes inside the cylinder. So we have a couple definitions here. The displacement volume is the volume that is displaced as the piston moves from BDC to the top dead center. The clearance volume is the volume left inside the cylinder when the piston's all the way up at TDC. We can calculate what the displacement volume is here from the bore and from the stroke. The total displacement volume is equal to the displacement volume for one cylinder multiplied by the total number of cylinders in an engine, usually ranging between 3 and 12 cylinders. So for example, if an automotive engine specifies that there's a 3-liter V6 engine, that means that the displacement volume per cylinder is 500 cc, or 500 cubic centimeters, which is half a liter. Now the important parameter is called the compression ratio of the engine. That's a ratio of the two volumes, so the minimum volume and the maximum volume. This is important because it determines the performance of the engine. Here we see on a PV diagram the cycle which an engine goes through, where the net work is the area inside the curve. As a performance indicator of the engine, one thing we define is the MEP, or the mean effective pressure of the engine. So the MEP is a fictitious pressure that if it was acted on the piston for the entire power stroke, it would produce the same amount of net work as is actually produced in the cycle. So on that right, if we look back at the PV diagram, which goes between the two volumes, the area under the rectangle defined by the MEP has the same area that's in the actual curve where the net work is. So these two areas are equal. This is the 4-stroke cycle for a spark ignition engine. You can see the PV diagram on the left, and on the right the 4 stages or the 4 strokes. So first we have the compression stroke, and in the compression stroke the piston moves to the top, or the TDC, and the fuel and air mixture, which is inside the cylinder, gets compressed. The second stroke is the power stroke. So with spark ignition, the fuel and air combust, the piston moves down, finally the exhaust stroke, and then the intake stroke. So the ignition is done by a spark in the power stroke. In the exhaust stroke, the exhaust valve is open. The products of combustion are exhausted out the engine. The intake stroke, the intake valve is open, and a mixture of fuel and air enters the cylinder as the piston moves down to BDC. So here's everything labeled on the PV diagram. Where the valves open, where the spark ignition occurs, where combustion finishes, and here are the 4 strokes labeled on the curve. We idealize this to do thermodynamic calculations, and we had idealized this in a cycle called the Otto cycle. And this is for spark ignition engines. So the air and fuel mixture is ignited by the spark. When we idealize this, we assume that we have an ideal gas in the cylinder, and we assume that the ideal gas is air. We can assume constant, or we can assume variable specific heats for the analysis. The 4 stages of the Otto cycle consist of isentropic compression, constant entropy as the piston moves up and compresses the air in the cylinder. The second stage is heat input. We consider it constant volume heat input, or Qn, that represents the combustion stage. From 3 to 4, we have an expansion. In the ideal cycle, it's isentropic expansion as the piston moves down to BDC. So again, isentropic means no irreversibilities and no heat transfer. And then the 4th stage is heat removal at a constant volume. And you can see this ideal cycle on the left on the PV diagram. So here from 1 to 2 is the isentropic compression. From 2 to 3 is the heat input representing combustion at constant volume. 3 to 4 is isentropic expansion. So in the cycle, in the cylinder, the mass of air inside is fixed for the Otto cycle. There's no air going in, there's no going out. It's a fixed mass, therefore we use a control mass, not a control volume. So we call this a closed system. It's not a steady flow system, it's a closed system. So therefore, when we do our energy balance, or apply the first law of thermodynamics, we will get that the total heat input subtract the total work output is equal to the change in internal energy. So we can apply this balance to the whole cycle, or we can apply this balance to one of the four processes in the ideal Otto cycle. So in summary, in this video, we went over engine geometry, top dead center, bottom dead center. We looked at the 4-stroke cycle, intake, compression, power, exhaust. Then we looked at the ideal Otto cycle, which consists of compression, constant volume, heat